Welcome to lecture 7 of MCS 471 of numerical analysis. We will consider the golden section search method, which is a method to find an optimum inside a certain interval. So in a way, this is no longer a root finding, but very much related. So we are essentially closing off a chapter in our course. And if you are following the textbook, then we are making a quick excursion to chapter 13. So why is it nevertheless quite appropriate to see the golden section search method now? Because it's very similar to the bisection method. The bisection method was our first method for a root finding. So there are three parts in this lecture. We start with the mathematical derivation of the method, starting with a definition of our problem. Our problem will actually be a minimax problem. Try to get as accurate as possible, so that's the maximum, with a minimum amount of work. So we define algorithms, or we study algorithms in this course. Algorithms are defined in this course as Julia functions. So we start again, we restart, then again with specifying what is the problem. So more specifically, what is the input, what is the output of our Julia function. We document our functions, what are the essential parameters, what are the tolerances, and then we look at a run. So we will have one running example. And most importantly, we start from correct functions, but we also we want to analyze the method. In our design, we want it to be efficient and accurate. What does this now mean in practice? How fast is our method converging and at what costs? So let's do this. What is our problem? Well, we have a function that is continuous over an interval, and we call it unimodal, in the sense that there is only one minimum in that interval. So unimodality also applies to the maximum, but throughout this lecture we will search for the minimum. So we want that in each step we reduce the interval that encloses the minimum. So that's actually what it means to be a unimodal problem. We have an enclosing interval, and also we want to do a minimum number of function calls. So I was relating to the bisection method. We also actually don't want to take any derivatives. So this becomes a root finding problem if you take the derivative of the function. But similar to the secant method that we did in last lecture, we want to avoid taking derivatives. We have a running example. Here is a unimodal function over the interval 0, 1. So unimodal means that there is one unique minimum inside 0 and 1. And if you look at the function, take the derivative, you have the exponential -2. So take the natural logarithm of 2, and that's kind of around 0.6. So the minimum lies around here. All right, a very nice function, continuous. That will be our running example. And here is our first idea. Our idea comes from bisection. So we want to cut the interval 0, 1 in half. And how can we do this? Well, we can evaluate close around the middle. So we evaluate at 0.48 and at 0.52. So we have the green line and the red line where we make the cut. And you can see that as the function value at 0.52 is less than the function value at 0.48, we will actually cut the interval. We will be left with the interval 0.52 and 1. So the bisection method, similar an idea to bisection method actually applies. Let's try to see if we can find this. Well, here, like the bisection method, we actually have a midpoint. But if you would do this with a root finding problem, we would do the derivative at the midpoint. So in a way, you could see this idea also as doing the root finding problem. But actually, we can't really compute derivatives, but in a way, we are actually also applying the secant line. So we actually are looking at the slope on the line connecting x1 with x2. But we actually no need to compute this actual slope, we just compare the function values. So the rule is actually very simple. We continue with the left interval if the left point is less than the right point, otherwise we continue with the right point. Now we have a method, and so the method is mathematically well defined as long as delta is not 0. But numerically, we have an interesting problem here because we want to take the delta small enough, so it should not be too large so that the interval where the minimum is actually inside x1, x2. So delta should be small enough, but then also it should be large enough to actually still distinguish the function values. So this is a very interesting numerical problem because it's related how accurate can you evaluate your function, and also the function itself, is it a steep function or is it a flat function? Now we will not pursue these problems now because the method has a kind of a very undesirable property, is that in every step we actually need 2 function evaluations, and that's actually much more expensive than the bisection method. Now we are working with a very nice function, but in practice it may often be that these functions are the running of another program, so that actually these function evaluations are quite expensive. So can we do better? Can we actually get an interval reduction in every step with only 1 new function evaluation? It will turn out that we can do better. So let us look into what is the problem now. What is our minimax problem? So we want to minimize the number of function evaluations and at the same time maximize the accuracy of the minimum that we are approximating. So the enclosing interval needs to be as small as possible. Now we will require, so the minimax problem is kind of vaguely stated. And this problem actually solving in full generality, we will not do. We will narrow the problem down by adding an additional constraint. So in every step, the size of the enclosing interval will be reduced with a constant factor. So we call this factor C. So we are looking for a constant reduction factor C. So our interval starts with a b. In the kth step, we have bk minus ak. Now that gets reduced with a factor, a positive factor c less than 1. Why is this helping us? So it looks like we have a more specific problem now with an extra constraint. How can this be any simpler? Well, it will turn out that it is. So more specific questions are often easier answered than more general questions. Here is what we want to do. So this is now, we had the minimax concern. So the constant reduction factor concerns the accuracy, but we also want to recycle a function evaluation in every step. We only want to do one new function evaluation. Well, let's see what happens. So if we have these 2 points, x1 and x2, we compare 2 function values. The constraint that we have a constant reduction factor will lead to the definition of these points x1, x2. So let's examine the 2 cases. If the left function value is less than the right, then we can say that the left interval remains, so the interval a to x2, because we will recycle the x1. So x2 becomes now the new right upper bound. So actually you should see a picture here. We have x2 here, and here is a, this is b, so b and a. So and here we have x1 and x2. So you can see on this very crude picture that x2 is larger than x1. So we actually are reducing the interval to ax2. So that means that you can, with the constant reduction factor, so the length of the new interval is now c times b minus a, and that's also the length of the interval ax2, the new interval, and that leads to a relationship, or a definition, if you like, of the point x2. So if we want this constant reduction factor, then x2 is entirely determined by the bounds of the enclosing interval and the reduction factor. We do a similar deduction. So now I don't do the picture, but you can picture another case where the function value at the right is less than at the left. Then what happens is that by the same reasoning, the constant reduction factor, we then have a definition of the location of the left point. So the bottom line of the slide is that if we know the value for the reduction factor, then actually we mathematically know our algorithm. We know the locations of x1 and x2. This slide summarizes the previous observation. So we start with interval AB. We have 2 function evaluations, one at x1, one at x2. And whatever happens, either x2 remains or x1b remains, depending on the function values at x1 and x2. But in both cases, the remaining interval is c times b minus a. So in words, you can say that x1 lies at distance c times b minus a from the right bound b, and x2 lies at the same distance from the left bound. So this picture shows that the constant reduction factor determines the positions where you evaluate the function. And in some sense, this is nice. This is completely independent of the function now. So in some sense, it's a reduction of our problem as well. So the reduction factor was one simplification. Let's make it even more simpler. If we know how to do one case, the case where the left interval remains, then the other case is similar. So let's focus on that case first. And also, if we know how to do this on the interval 0, 1, we know how to do it on any interval. The reduction to 0, 1 will actually simplify the calculation of the reduction factor. So we have the general formulas for x1 and x2. So the reduction factor is actually now the length of the new interval. So that means that x2 is the reduction factor and x1 is 1 minus c. So in case where, so now actually I do need to make the picture again. So in case where we have something like this, where x1 is less than x2, we actually are reducing the interval. So now we have the interval c. So interval 0, c, we actually have to recycle the function value at x1. We have now a value for x1, it's 1 minus c. We have to take one new function evaluation. Do we take it to the left of x1 or do we take it to the right of x1, where x1 equals 1 minus c? There's only one answer, but we now pretend that we don't know it because we don't know the value of c. It will turn out that one of these cases, and here you see that case, that one of the cases leads to a reduction factor which is not very desirable, which is c equals 1 again. So here's the case. Suppose we recycle x1 and x2 is taken to the right of x1. Well, then we already know that in that interval 0, so we have the same formulas now. So once the reduction factor is known, the definitions of the points are known as well. So in particular, what happens is that C was the definition of the previous point x2. So if we take x2 now again to the right, then we have this same formula that we apply here. And actually we apply this to x1. So x1 can be remains where it remains to the left 1 minus c in the interval 0, 1. So this is this formula here. And once we define it in the interval 0c. So in the interval 0c, we actually apply the same formula. Here actually we have 1 minus c times 1. Here we have 1 minus c times c, because the right bound is actually now c. So this equation then would allow us to solve for c, and indeed it does, but the solution is actually rather trivial. If we solve this equation, we have c equals 1. So there is no reduction. So we actually end up with a contradiction. So if we choose the new point to the right of the previous point, of the point that gets recycled, then we have no reduction. So in case where the function value at x1 is less than x2, you must x2 consider to the right of the new function evaluation, or take the new function evaluation to the left of x1. Looks rather complicated in words, but we actually do have the algorithm now, mathematically defined. So now actually we take x2 to the left of x1, and we also rewrite x minus, so x1 in two ways. That actually leads us to a quadratic equation, and where we can solve exactly. So this shows that the reduction factor is 0.6 approximately. Not as good as the bisection method, where we have 1/2, but it is very, very close to it. So that is the mathematical definition of the golden section search method. I still have to explain why it is called the golden section search method. Well, in short, if you look at the quadratic equation and you add 1 to the root, then actually you see that we have the golden section, the golden ratio, the same ratio 1.6 that we found with the CCAT method, in the analysis of the CCAT method. So that is the mathematics. Recapping, perhaps I should scroll back. The picture that you have to keep in mind is this picture. So we have an interval AB, and each time we determine a new function evaluation, we compute a new function evaluation, and the invariant in our loop will be that the points x1 and x2 lie at fixed distances from the left and from the right bound. So that's actually the picture of the mathematical picture of the mathematical foundation of this golden section search method. So let's keep that in mind, and that's the important picture. So let's now go to the algorithm. So before we start with an algorithm, we have to define what is the input, what is the output. Well, we have a unimodal function, so the function must be given, and the function lives on the interval. So it's a continuous function, unimodal with the bound. So we have three essential input arguments. Then we have the numerical parameters. We have the number of work we want to do. So here we will say we do not want more than n, capital N, number of function evaluations. So the n always needs larger than 2. So we start with 2 new function evaluations. We have 2 tolerances, one tolerance on the accuracy or the forward error. So the forward error is actually the error we care most about. So this is why we call it the forward error. It's the length of the enclosing interval. So that's the delta. Then we also have the backward error. And the difference between the two is to take into account functions, the shape of the functions. So if we have very, very flat functions, then actually the tolerance for the backward error will actually be easier satisfied than the forward error. So the backward error, again, how much should we change the input function so that we do have, so that the approximate input is actually the exact answer to the modified problem. Okay, so in the next slides, I will gradually So we have specified now the problem, the input and the output. We will now document the function, and then we will define it, and then we will run it. So there are 4 stages. They are here represented as one after the other. In practice, you start running as soon as you can in a test-driven development. All right, Julia is nice in the sense that it invites you to document functions before you write them, so even before you get to the prototype. So we repeat the specification, these functions. So we are looking for the minimum here of a continuous function defined over an interval. We will not do more than n function evaluations. And we have, so that's our first stopping criterion. And the 2 other stopping criteria are determined by tolerances on the length of the interval and also on the difference between the 2 function evaluations. All right, so we can do this a little bit more formally. So we have 3 essential parameters and 3 optional parameters. So sometimes it's good to give default values. We will define, we also give an example. So we have a running example in our mind. So in a way, this documentation, this slide here, recaptures the running example. So we have an example in mind where we actually know what the optimum is, and it's a nice continuous unimodal function over the interval 0, 1. All right, the method may fail. It may fail to reach the accuracy, but we still then return the bounds of the enclosing interval. The method will be verbose, so the function here will actually do some printing. So that could have been a last output, a last input parameter that we could have toggled off the verbosity. Okay, the important statements before the loop are actually the first 5 statements here, where we define the constant c, so we actually compute it here. Formally, we could also have had the constant 0.618 embedded in there. So you can see that when C is defined, then the 2 first function evaluations are defined. And they will be stored. We can then actually already print out our first line. So we have the locations, so with string interpolation, we have the 2 locations. They are printed with a precision of 4 decimal places, so 4 places after the point in scientific notation. So the method is actually not a very fast method. So 4 decimal places here will suffice for our running example. So the working precision is higher, so we compute with 16 decimal places, but we only show 4. This is uniformity. All right, so this is before the loop. As you can see, there are 4 or 5 essential instructions. The other instructions concern the nice printing. All right, so then we do have the loop. So we will not do more than n function evaluations. We have already done 2. So this means that we only have at most now n minus 2 steps. We do one new function evaluation. So in the mathematical derivations, we focused on this case. So in case, perhaps I should make the drawing again. So in this case here, we have a function that has this shape, where here we have x2, and the value at x2 is larger than x1. So that actually means that we recycle x1. So and that x2 becomes the new right bound. So this becomes the new b. This function evaluation now becomes x2. So that's what's happening here. We also relabel the function evaluation, and then we recalculate the x1. So we are going to take one new function evaluation. So let me draw this in a new color. So the new x1 will be to the left of the previous x1, which now has become the x2. So we have the x1 that we compute with the formula, the fixed formula that we used before the loop, and then do the function evaluation. So the main expensive step is actually over here. So as an exercise, the first exercise, I will let the justification in the else entirely up to you. So the first exercise asks to redo the mathematical derivation, now in case where you have the other shape. So make a picture and justify the statement. So in the else case. So in the mathematical derivation, we actually focused on the if case, when the if is done. So in the first exercise, you will describe what's happening in the else case. So that will actually essentially complete the correctness proof of the algorithm. So the algorithm that gives you a constant reduction factor C at the expense of one function evaluation. You can see that only one block of statements is executed, and in every block, either the if block or the else block, you do one new function evaluation. So in the loop, at most n-2 function evaluations are done. So that's another statement on the cost of this algorithm. This algorithm encoded in the Julia function will do no more than n function evaluations. All right, it can do less than n function evaluations if this stopping criterion is satisfied. So here we break out of the loop with a return statement. We break out of the loop if one of the conditions is satisfied, or they could be both satisfied, when the length of the interval is less than the tolerance. So in some sense, the absolute value here is actually redundant, as b is always larger than a, but here it is necessary. So for symmetry, the absolute value is in both cases because they are positive numbers. So if this is an OR statement, this pipe here, so if one of these two or both of them is satisfied, then actually we will terminate the loop. And we will report false as failure. If we have to go through the entire loop, if the stopping criterion was never satisfied, then we have a failure. And that is indicated by the true here. So for this lecture, there is the function that is posted. So that's what you will need to use in the exercises. All right, so we understand the mathematical property of this golden section search. We have a constant reduction factor of 0.6 at the expense of one extra function evaluation per step. Almost as good as the bisection method. That's the main mathematical result. So let's now see how good this is. So I have coded up the golden section in a separate function, in a separate file without the main program. So you can either write a new main program, or note that in the Jupyter notebook, we actually do not write any main programs. We actually just have these two statements. So in an execution cell in the Jupyter notebook, you actually copy these two statements. In a separate cell, you copy and paste the code for the function GSS. Here you see that the default parameter was 20 function evaluations, but already the length of the interval actually became less than the given tolerance of 10 to the power minus 2 after 7 steps. All this succeeded after 9 function evaluations. On this example, where we also have a 0.6 as the minimum. So you can see that, well, the 0.6, we have actually an enclosing interval, which is kind of, here you can actually see what the function values are. And so we have the function values that actually are making that the stop criterion of 10 to the power minus 4 is actually satisfied. So you see that 4 decimal places in the function value are the same. This is very close to having 2 decimal places correct. So if you would round, you would actually see. All right then. Second exercise. So the function was called on our running example with the default value of the tolerances. Here we consider, so the purpose of the next exercise is that we consider 3 different functions over the same interval. And the functions are such that the minimum is 0, so what the answer is. But if you remember a little bit the shape, so we start with a parabola, then we have x to the power 4 and then x to the power 8. So over the interval, the functions actually are getting flatter and flatter. So if you take the picture, you have the parabola here, then you have the quartic, and then you have x to the power 8. So the functions are getting flatter and flatter. So that will mean that the difference between the function evaluations will start to determine the stop criterion. You will actually observe this in the first part of the exercise. So the first part of the exercise is running the function, observing what happens, and you will indeed see that as x to the power 8 is flatter, you will actually see that the number of function evaluations should be less than with x to the power 2. Now the second part asks you to change the default tolerances so that the end result, so the enclosing interval, is actually the same. So the accuracy where we actually really care about is actually the length of the enclosing interval. So what you need to do is you need to change the default tolerances. Typically, you make the tolerance on the backward error, the tolerance on the difference with the function evaluations smaller. All right, so that actually concludes also the second part. So we have a function, an algorithm that we can execute. Let's now look at how this method behaves, and actually this is already my last slide. So the cost and the convergence is actually again summarized in one sentence here. We have a derivative-free optimization method that gives us a constant reduction factor of 0.6 at the cost of one new function evaluation. So the last exercise is very similar to one that we had with the bisection method. Suppose you are starting with one place correct after the decimal. So the length of the interval, you have one decimal correct, and you want 4 decimals. Suppose that you start with the interval 0 and 1/10. After how many function evaluations would you need for the length of the enclosing interval to be 10 to the power minus 4? So you can start with this exercise. So this exercise can be solved independently. So one can look at the first sentence and apply that property. You know that you have already 2 function evaluations, but so let's start from the one extra function evaluation. We'll actually multiply the 0.1 with 0.618. So you can solve this by just multiplying by C, or you could do it a little bit more systematic by saying I'm looking for a value of n such that so I can write down the equation. So we have C times 0.1. So that's the beginning accuracy. And we're looking for the n here. So if we do this once, we will have that the accuracy is improved with this factor C. So actually the exercise asks you to solve this equation. So you can take a logarithm and then solve for n. So that's the exercise. You can also do it experimentally. If you're more an experimentalist, you can actually look for an example and run it. The 0.6, so without doing any calculations, you can also estimate. We've seen that with the bisection method, where the reduction factor is 1/2, so 1 bit per step. There you need about 3 or 4 for 1 decimal place. So here we start from 1 decimal place and we want 3 additional decimal places. So it takes at least 3, but you can now say 4 here. So you will definitely need at least 10 to 12 function evaluations to reach that accuracy. All right. Then so this was a nice conclusion of the first chapter on root finding. So the golden section search method is a very robust method, a very simple method, similar to to the bisection method. There are many, and it also actually, it's a rather primitive method, because we only use 2 previous function evaluations in every step. In that sense, it's a 2-step method, like the secant method. For the first computer project, you consider Muller's method that uses a parabola to find a root. You can also do something similar here. So Muller's method actually also applies here. Instead of comparing 2 function evaluations, you could actually take the last 3 function evaluations and always take and then construct a parabola through these 3 function evaluations. We will not pursue this here, but in practice, if you ever have to solve, do an optimization problem, know that there is an entire family of methods, and here actually this is a classical subject. So here I gave one of the rather classical papers. But if you think about this, if you remember the improvement of the secant method with Muller's method, then you will also see how you can improve the bisection method with relatively few work, actually. But we will not pursue this here. All right. This concludes this pre-recording on the golden section search, where I want to point out that the important statement is actually summarized over here.